Alright, hi everyone. Today I'll be gonna be talking about the programming ZKP part 2, continuing from the last section. Last time we talked about the programming ZKP from zero to hero. It's coming from the zkintro.com section. So the content is gonna be recapping of the previous site, prime factorization and one-way functions, and setting the constraints for our circuit and answering some questions. So if you're watching from Twitter, I'm going to be cutting off some parts, but if you're interested, you can watch full the video on YouTube. So we're going to be continuing now. So okay, last time we talked about what is gross 16 and how the whole cryptographic schemes are going to be working. So first of all, we're going to have processing step. So we're going to be creating trusted setup, generating source strings, CRC. I forgot the name completely, but we're going to be generating the toxic waste. It's called toxic waste. And then, so this generated trusted setup, what we are going to be creating is we're going to be creating verification key and proving key. And then we're going to have arithmetization part, which is technically a creating circuit. We have the problem, we're going to be creating a circuit. So we'll write it in circom, and then we will build the circom. Once we build the circom, we will have R1CS. That's the binary form of the whole circuit, and we're gonna have the WASM file, which is gonna be used to generate the witness. And then we have to generate the proof. So we're gonna have the input, witness, and proving key, which is Z key. So and then we're gonna have the proof. Then we will verify it. So let's check it out. That was the recap. So that's the simple circuit we created last time. What we did was we're gonna be taking two inputs, which are gonna be private, and then we're gonna be outputting one. We're gonna have one output. We just have to set two multipliers and two values, multiply them, and out. So what we were saying is, by definition, we were saying we know two different, like we know two values. The output is gonna be 33, or this is how we're gonna be proving we know two values. The output is gonna be a certain number. So that was what we created last time. Now the problem from here is it's called prime factorization. Okay, what is prime factorization? Prime factorization is any given number, we can be consisted of the powers of the prime numbers. This is, I think, the basic school math, 3 to the power of 2. So this is how this random number can have the factors, prime factors. But however, we also can have this number itself and times 1. That is the problem, because in our case we are trying to set up this to a smaller number, but this output is technically known for everyone, because the whole problem we are saying is we know two values, and the multiplication of this are going to be 33. So the cheaters can say, okay, 33 times 1 also can be a 33. So that's how they might try to set it up, or they might try to cheat the whole system. But in our example, we did not check it for 1. We did not set any constraints that any of the inputs cannot be 1. So we are going to be doing that now. Also, another quite interesting stuff here is the prime factorization is going to be really good example for one-way functions. What does it mean? Because if we have the bigger number, we don't know which numbers are the prime factors. It can be the prime factors of this number. For example, let's say if this number 20,475 can be the multiplication of all, or it can be the multiplication of this 2, or it can be multiplication of this whole 3 times 9, or it can be, there are a lot of variations, so it's hard to know which of them. So because we cannot compute it backwards. But however, if we have these two numbers, we can multiply them to each other and we can create the sum. Oh, not the sum. We can create the the result. So to one way to multiply each numbers and creating the result is easy, but from the result finding out which two of them are are creating this result is very hard. That's called one-way function. That's how the cryptography works technically. So the solution, that's how the solution is going to be. There is a is0 library from the circumlib library. We are going to be including this library, and we are creating a component which is called is0 check. So we are technically adding another circuit, another component in between these two inputs, A and B, and we are inputting two of them as an in and one of them as an out. So what does it check is zero. How is0 works is it's gonna take any number. If it is 0, it results 1. If it's not 0, if it's non-zero character, it results to 0. So what we are doing is we are trying to create a way if any of these are 1, let's say if A or B is 1, the result is going to be 0. And then we are saying constraint that out should be 0. So it is quite confusing, but if any of these values are 1, or A or B is 1, so which means whole multiplication is going to be 0, and the output of the function is going to be 1. So we are saying no, it should not be 1, it should be 0. So it means this whole multiplication should not be 0. If A or B is just any numbers, this whole constraints is going to check, and then we will assign the value C as a solution. So let's check it out. I'm going to show you how I did. So I am sure my terminal is open, so you can check it out from the ZK intro section. Everything is recorded there, so you can just try to follow it and it will be easier. Let's check it out. First of all, I have done over everything. Let me show you my example 2. And if you see this, sorry, I cannot make it bigger. Nope. Here it is. I'm sure it's more visible than before, but here is how it's starting. That's how it is. I have implemented the same things, exactly the same thing, and I have already built that as well. So what I have to do is just the generating proof. Generate proof example 2. Oops, we have an error. Why we have an error? Because there is a problem. What the main problem is, in the input JSON file, I have added like A and B as 33 and 1. Because B is 1, it's failing. We cannot even generate proof. Now if I switch it back to its original forms, now we try to generate proof. Yep, this is the proof. And now we will verify. Example 2. Snarks. Okay, here it is. It's verified. That's all. That's how we tried. That's how it fails. That's how it checks up. But before, in the example 1, because I can try to show you in the example one. Let's check it out. Example one. Example one, and I can show you. Let's check it out. The input first. Okay, let's make it 33 and 1, and we should try to use just generate proof example 1. It is working. It generated proof, and we're gonna check it out. Just verify proof example 1, and it's okay because there is no any constraints in example 1, but in example 2 we checked it, we modify this, and it checks the constraints and it works. So that's technically all for today. I think it's been quite long, but if you've been watching till the end, thank you. See you in the next video, not tomorrow because I am not recording the videos every day. So bye bye.